Mathematica and the Raspberry Pi. Amplitude modulation. Amplitude modulation is one of the oldest and simplest forms of modulation. Here we define the modulation index, the basic modulation frequency, and the carrier frequency. Over here, we have the equation which defines the analog modulation waveform. And these last statements indicate the range that we're going to plot and a couple of labels to make the plot a little bit more understandable. So if we run it, this is what we end up with. Basic amplitude modulation. It's very easy to transform this basic plot into something which is interactive by using the manipulate function. To do this, we start by relocating our three parameters of the carrier frequency, the modulation frequency, and the modulation index to the bottom of our code. And we define their characteristics as, let's say in the case of the carrier frequency, the default position, 15, the minimum frequency, 10, the maximum, 20, and the increment of, let's say, 1 Hertz. If we add the command appearance labeled, what that means is that it will actually display the numerical value of the carrier frequency when we adjust the slider. To make this plot a little bit more interesting, we're not going to just simply plot the carrier frequency by the AM signal by itself, which is this part of the plot command right here. But we're going to add to it this piece, which is just simply the modulation envelope, and this piece, which is the modulation index. Now, so that it's easy to separate these three different plots, we're going to give them all a label. And we're going to do this by using the plot legends command. And we're going to call them AM waveform, modulation envelope, modulation index, and we're going to put it at the bottom of the manipulate window. Let's see what happens when we do this. And there we have it, the AM waveform displaying three things: the waveform itself, the modulation envelope, and the modulation index, all of which are adjustable. So notice what happens. We can adjust the carrier up or down. We can vary the modulation frequency. Notice we can even put the modulation frequency down to 0, in which case there is no variation at all because DC has no frequency component. And the modulation index, you can vary, let's say, from 1, which is 100%, which means that at some point the carrier signal actually disappears at this location here. And this is the greatest degree of modulation we can use before distortion sets in. Or we can back off at 50%, even lower. And of course, if we have a modulation index of 0, then there is no variation whatsoever, and the modulation frequency is irrelevant because it will have no effect on the carrier frequency at all. We will now plot the AM signal in the frequency domain, and it will consist of 4 components: the original modulation signal, which is simply the baseband, the lower sideband, the carrier, the upper sideband. And then we're going to label these signals. So here they are. These are the signals we're going to be labeled. We put them into a string, and then we're simply going to plot them with these names. And the result of this looks like this. And here we have it, the AM spectrum. We can vary the carrier frequency up and down. We can vary the modulation frequency. And we can vary the modulation index. And there we have it, amplitude modulation.